Huh? It worked first try. Today is going to be a red letter day. I'm going to probably be able to eat popcorn without it getting stuck in my throat. Wow, I've never had that happen. But when the technology works on the first try, today could be the day. Today could be the day. In fact, if I read my horoscope today, it probably said, if you have an irrational fear of popcorn, today's your day to face your fear. I haven't read that either. I usually don't read that. Anyway, let's go to number 14. This guy looks a little bit like Ebbinghaus, doesn't he? Not really. Okay. This is not Ebbinghaus. This is an Italian guy called Pareto, Vilfredo Pareto. Okay. Pretty cool name. He departed in 1923. But prior to departing this earth, he gave us this equation, which is much like Ebbinghaus's law of forgetfulness. Okay. This one here models what he called the Pareto Principle. So if you come up with a theory or a principle, you can name it after yourself. And what it does is it basically describes the disparity of wealth, in this case, in any given nation. Also known as the 80-20 rule, which basically, in terms of wealth, says 80% of the wealth is owned by 20% of the population. So the rich get richer, possibly the poor get poorer, and the middle class picks up the tab. Right? That's the American dream. So in 2011, there was this movement called Occupy Wall Street. And basically had all these people that quit going to work or they were unemployed, and they were going to show Wall Street how unfair they thought the disparity of wealth was. So they would stand on the street corners, and they would dress up in these Guy whatever masks. I forgot what his last name is. It's from V for Vendetta, but it's a mask that's modeled after a guy named Guy, a French guy. Does anyone know his last name? Thierry? Oh, yeah. Slave of town! I guess that's what he says. Okay. But anyway, there's a little bit of irony here, because these are the people that were in the middle of a work day, were not at work, because either they were skipping work or they were unemployed, and they were standing on the street corner talking about how they didn't have any money. Kind of interesting. And they were trying to change the world, but they didn't want to show their faces. But there was kind of a catharsis in community griping, right? They all looked the same, and we are the 99%. So they were basically making the claim that the 1%ers had all the money, and the rest of the 99%ers were like these people, which is not really true, because most of the other 99% were what? At work, making money. Too busy to do this. So anyway, dripping with irony. The only thing I think their movement accomplished was to raise the sales of these V for Vendetta masks and hoodies. Okay, the demand for both of those went up. In fact, I think later that year, this was a very popular Halloween costume, which means that they were being parodied. Kind of sad. But again, the American dream, capitalism. But anyway, here's what he said. He said that in any given situation, 80% of the outcomes are determined by 20% of the inputs. And when you're talking about wealth, 80% of the population owns 20% of the wealth. So this is a log equation. It's base 10. Social scientists use base 10. And let's see what these variables are. P ends up being the population of people owning a certain amount of wealth. Okay? C says that it's the actual population of the country. K is the Pareto's constant, which should be given to you. And much like Ebbinghaus's law of forgetfulness, kind of depends on the country, depends on the situation. And W. W is where I forgot to add an important description here. W is the wealth level that an individual has, and here's what I should have said, in millions of dollars. Okay, so we are measuring wealth in millions of dollars. The population of the country, though, is not measured in millions of people, but in actual people. So, and I kind of clarified that later on. But when I wrote this question, I actually looked up some real statistics, and I formulated the question so that it is indicative, more or less, of what actually is happening. So these aren't just specious numbers. They're ripped from the headlines, if you will. Okay? So part A, solve the equation for P. So much like we did for Ebbinghaus's law of forgetfulness, we have a literal equation, or a formula, and we can solve it for any one of the unknowns. In this case, we have 4 unknowns, and if you solve it for a particular unknown, that means that you are going to be evaluating it more than likely repeatedly, and you don't want to have to plug in and solve every time. So you solve one time, and then it's plug and chug. All right, so we want to solve it for P. And just like we did with Ebbinghaus, we're going to focus on the right side first. We're going to condense it because they're both log base 10. So first thing we have to do is bring the K up as an exponent. So you have log base 10 of C minus log base 10 of W to the kth power. And now since they're both log base 10, we can pull one log out front. The positive terms argument gets multiplied in the numerator, and the negative terms argument gets multiplied in the denominator. So it's C over W to the kth power. And the left side is just the same as it was in the beginning, log base 10 of P. Now, yesterday, we exponentiated both sides base 10, and that still works. 10 to the log base 10 of P is just P. But there's another way you can actually accomplish the same thing. You can actually use the fact that logs, like exponentials, are 1 to 1. So remember, if we have like b to the x equaling b to the y, we could say that x equals y, because exponentials are 1 to 1. Well, logs are also 1 to 1. So we had this property in 4.3, but we haven't used it yet. Log base b of x equaling log base b of y implies also that x equals y for the exact same reason. Logs are exponentials. So it's just another way to accomplish the same thing. You have log base 10 of blob equaling log base 10 of blob, so you can equate the blobs. In this case, P equals C over W to the kth power. Now that is a more user-friendly version, especially if you're trying to find different values of P, because there's no logs in it. But it's still loggy, right? It still has the genetic DNA of a log because there's an exponent there. So that takes care of part A. Now part B. Now we're going to use it. It says if the population of the United States is considered to be 312 million people, and in 2011 I believe that was pretty darn close, plus or minus maybe, several million. Census data is not always accurate, right? Blarf and Garf. So what letter is this going to be in our equation? The population is C, right? So in this equation, we're going to let C equal 312 million. And I actually clarify that. That is, let C equal the actual number, 312 with 6 zeros. Bless you, bless you. We're given the constant, which thank goodness, because I wouldn't know what to use for it if they hadn't given it to me. What percentage of the U.S. population has $20 million or more? So $20 million or more is going to be our value of what? W, it's the wealth level of the individual. Yes, thank you for answering that. So this is where it got a little confusing, because if you actually use 20 million, which is what you might have inferred because it didn't say otherwise, when you plug it in, you get a number for P, the number of people that have $20 million or more in the United States, to be a very, very small number. In fact, much less than 1. So could it be that that's true? That would be like a part of a person. A part of one person has $20 million. That would be like some guy's finger is worth $20 million. Maybe, right? Yeah, Goldfinger. What was his name? Yeah, Goldfinger had a gold finger, right? Which, if that was King Midas, then he might also have a gold nose. What? Yeah, did he pick his nose? I don't know. But that reminds me of a funny joke. Why are monkeys' nostrils so big? Because they have big fingers. I don't know if that's the best joke in the world, but I just thought of it. All right, so it's probably a not realistic number. So with the new information, we're going to use 20 for W, 20 million. And now all we have to do is plug and chug. So we get P, the number of people in the United States. The number of people in the United States is going to equal 312 million all over W, which is 20 to the kth power, 2.824. Now that is an exact answer, right? What are the units of this answer? People, okay? So if you were one of those Occupy Wall Street people, you might put that on your picket sign, right, and go stand out and say, this many people have $20 million or more, and I'm not one of them. People are going to drive by going, I'm on my way to work, but look, oh, yeah, no sympathy at all. No sympathy at all, because I have no idea what that number is. I have no appreciation. Is that a lot of people or is that not a lot of people? Not the best way to get your message across, right? You might want to use numbers that people understand, which are typically integers, right? So that's where, guess what comes in? Calculator. I can. Can you? I can get it down to the nearest 10,000 in my head, which is 66. And no, I can't do that on my head. I just remember what it was from last period. But every magician has his tricks. And I'm missing a 0, by the way. I'm missing a 0 on here. There we go. And then divide it by 20, raised to the 2.824. A 1, 2, 3, a 1, 2. The polka is not complete without the third 0 on the second half. Yeah, very good. Thank you. I actually don't need parentheses. I didn't put that extra 0. So let me just multiply by 10 after the fact. I'll fix it. There you go. You don't need parentheses because I'm dividing by 20 raised to the power, and your calculator knows your dear Aunt Sally very well. And your calculator would do exponentiation before division. Now, again, Riley, it's better to have them and not need them than to need them and not have them. Yeah. So safety first, right? But sometimes you don't need to put on your safety goggles if you're just like gluing something. Right? But safety first, right? So anyway, that comes out to be 66,000. I forgot what it was. I was thinking of a construction joke. 076. Now, if this were a test question and you had your calculator, guess what answer choice A would be? 66076. And you might get that and be like, dang, that's a lot of people. That's a lot of people that have $20 million. I'm not one of them. And you would answer that and get it wrong. Why? Oh, very good. Never walk away from a problem until you've actually answered the question that is being asked. They are asking us to figure out the percentage of the population that has that much money. So how can I turn that number into a percentage? Yes, you take that number, which we will round to the nearest whole person, and we'll divide it by the entire population, which the number is the same number we used in the calculation. If like 5 more people were born in the United States in the process of doing this calculation here and this one, we're not going to add 5 to it. Okay? We just want to use the same number. 3, 1, 12, 0. And then to convert it, that number to a percentage, you'd multiply by 100. Okay? And if you do that, let's see what we get. We get that number. And I'm going to actually use all 5 decimals here just to be a little bit more accurate. And we'll divide it by 3, 1, 2, 0. I'll get them right here. 0, 0, 0, 0, 0. Right? But if I multiply by 100, won't 2 of those go away? You want to do it that way or you just want to multiply by 100? Let's just multiply by 100. And you get there. That's your answer. So that is 0.021. We'll go to 3 decimals. Now that number looks funny because it looks like that number then should be converted to a percentage by multiplying by 100 again, right? Which would put it at like 2.1%. But that's not right. This is the actual percentage. Okay? It is much less than 1%. 0.021. That is what? What would you, if you read that correctly, that's not 0.021, that's 21 thousandths. 21 thousandths of a percent of the U.S. population has a net worth of $20 million or more. And I'm not one of them. So I think I'm going to complain and see if I can't get some $20 million. Okay? I'm going to go pick it. I'm going to skip work, and I'm going to go pick it. But you know what? I can't even do that. You know why? Because I need money for a mask and a hoodie and for sign-making materials. And you can go to Hobby Lobby, You can get carried away with sign-making materials. And I don't have the money, so I can't even pick it. I can't even complain about not having money because I don't have the money it takes to buy the picketing paraphernalia. What to do? I guess I'll just go to work. Let's go to work. Tomorrow's Inauguration Day. Okay. I think Trump's in here, right? Trump's one of those. So he claims. Yeah. I don't know. He hasn't released anything, right? If you take his assets and you measure his liabilities, I don't know. Maybe it's not greater than 20 million, right? Maybe it's not greater than 20 million. Anyway, Occupy Wall Street. Why is it called Wall Street? Yeah, there used to be a big wall there. Yeah, it was a defense wall. To defend against aliens, outsiders. Yeah. Okay. Any other questions from the worksheet? This is all we're doing today. Did we not answer it? Oh, how does it make you feel? Sorry. How does it make you feel? It makes me feel pretty good because I can get into that leap percentage living here in America if I really wanted to. We have upward social mobility here. It's not as easy for some as it is for others, right? You have to overcome obstacles, but you can't let the obstacles become the excuses why it doesn't happen, right? Speaking of walls are put there to keep the people out who really don't want it. Okay? Sometimes the wall is just in front of you and you complain, but it's just a wall that's like barely wider than you are. And all you have to do to get on the other side of the wall is just walk around it. But some people focus on the wall so much that they can't get over the wall, much less around it. Arrgh. So yeah, I'm thankful that we live in America where we could, with enough hard work and redoubling our efforts, and maybe some help, not handouts, but maybe hand-ups. Yeah, we can make it. All right, so it makes me feel that way. Bridget, how does it make you feel?
I feel good because I don't think America needs that much for everybody, because then everybody would try to buy everything, and not everybody can have everything.
Right. I mean, if you look at Black Friday, that's how it would be every day, everywhere. Who wants that? There'd be no place to park. Yeah. I forgot who it was. It might have been some comedian. I forgot exactly who it was. You can have everything, right? Where would you put it? Maybe it was George Carlin? I don't know. You can't have everything. Where would you put it? Mini storage. Mini storage. Hey, what are you doing this weekend? I'm going to go visit my stuff at the mini storage. Go visit it. What's up, stuff? See you next time. All right. Any other questions from the worksheet? Now's your chance. Any of these could appear on the test next Thursday. Which one, Croner? You didn't know what you were doing on which one? Number 11. All right, number 11. Y'all ready? Number 11. 12. 11. All right, so 11 is very similar to what we just did, but we're doing it many times. I'm not going to do all of them, but let's look at... I've always been bad at numbers. I apologize. Use the properties of logs to prove that that equals that. You may want to eventually multiply by a clever form of 1. You're welcome for the hint. You're welcome. Yeah, it was challenging and fun, right? It's not fun to overcome challenges? Don't you feel good when you overcome a challenge? There you go. So challenging and fun go hand in hand. You can't have one without the other. Right, good. Okay, so we talked briefly about how to prove something. The easiest way to avoid cross-contaminating the both sides is to draw a line down the middle. And what you're going to do is you're going to work with each side independently as expressions and try to manipulate one to look like the other. Okay, so we have to show that one of them equals the other. All right. Is it easier to build a house or tear down a house? Tear down a house, right? Because to tear down a house, all you really need are a hammer and, of course, your safety goggles, right? But to build a house, you need your safety goggles and lots of specialized equipment and specialized knowledge, yes? So with that in mind, it's easier to tear stuff down than to build stuff up. So you want to start on the side that has more information, which appears to be which side, Blake Fain? Which side looks more complicated to you? The left. Why? That's what I would say. Very good. It has one extra negative factor in the front. So let's go ahead and start on the left, and now our target is the right side. We're going to manipulate the left side to make it look like the right side. And we can only manipulate it by using properties of logs, adding a clever form of 0, multiplying by a clever form of 1. So with a negative 1 out front, what can we do with that negative 1? Sorry. The property that allows us to bring up coefficients and put them as exponents, we call it property 3. So let's try that. That'll become the natural log of x minus the square root of x squared minus 1, all to the negative 1's power. Yeah. It's already looking the same, right? Are we done? Does it look the same? No. Okay, next question. Do some obvious algebra if there's any to be had. Can we distribute the negative 1 to both terms? No. It only works if they're factors. Well, what can we do? Flip it. Good. Anything to the negative first power is the same thing as that, 1 over, that thing. Sweet. And now it's looking a lot, no, it's not like the right side. Okay. But, hey, at least we now have a denominator with 2 terms, and one of them has a radical. And we've done this year. What could we do to get rid of the radical, which is now in the numerator? Our target is to get the radical in the, it's in the denominator now. We want to get it in the numerator. What's that called? Remember when we had like 1 over the square root of 2? We would multiply by square root of 2 over square root of 2 to eliminate the radical from where it currently is. That's called rationalizing, right? And it gets rid of the radical from either the denominator to the numerator or vice versa. What if you had 1 over 1 plus the square root of 2? How would you rationalize the denominator? Now that it's 2 terms, you'd have to multiply by the what you get. Good. You'll always remember that. That's great. The conjugate over the conjugate. That's what we need to do right here. We want to get rid of the radical from the denominator and put it into the numerator because that's what it is on the right-hand side. So inside the argument, we're going to have x minus the square root of x squared minus 1, and we're going to multiply by a clever form of 1. And that clever form of 1 is the conjugate of the denominator, which is x plus the radical over itself. X plus the radical. Now, if you look at what we're trying to accomplish, that's going to put us in pretty good shape because I want an x plus the radical in the numerator, and now I have the x plus the radical in the numerator, and I want to get rid of the radical from the denominator, which is exactly what rationalization does. So on this side, if I multiply straight across, I get x plus the square root of x squared minus 1, and in the bottom I have the product of 2 what you get? Conjugates. So let's see what happens. It's going to give us a difference of squares. X times x is x squared. What happens to the inner and outer terms when you add them together? They cancel, right? They cancel. So you're going to have an x radical minus x radical. They're gone. And we're left with just a negative radical times a positive radical, which is negative radicand. And here you have to be careful because the radicand is 2 terms, and there's a minus out front you'd have to eventually distribute. So some very meticulous algebra going on here, which we practice like crazy in the beginning of the year, right? With a capital C at the front and the back. Crazy. X plus the square root of x squared minus 1. In the denominator, what happens? If you distribute the negative, you get x squared minus x squared, which is what? 0. And then you get a negative 1 times a negative, which is positive 1. Now, anything divided by 1 is just itself. So you end up with the natural log of x plus the square root of x squared minus 1. Is that what we were trying to prove? Yes. And so we're done. And as I mentioned in class, when you're done, you could write at the bottom, if you wanted to, QED, which is math lingo for bring it on, right? Or next, please. Which really stands for what? The Latin phrase, quid erat demonstratum. That which has been demonstrated. I showed it. You asked me to show it. I showed it. QED. I'm done. That was fun. Maybe not so easy. I wouldn't call it fun easy, but fun nonetheless. We're going to be doing a lot of proofs when we get into trigonometry. This is called an identity. An identity. They are equivalent for all values in their domain, so they are mathematical synonyms. You don't like the way one of them looks, replace it with the other one. You don't like the way the other one looks? Sorry, you're stuck with at least one of them. Any others in the time that remains? We've got 4 minutes. Eight C, yes. That's a cute name for 8. 8C. Use the properties of logs to condense. All right. Yes. So we didn't do anything like these in class, but I don't have to do an example of every single type and steal everybody's thunder. Y'all are thinking people, right? You can figure it out, especially with the hint that I give you. You can only condense your logs if the bases are the same. Our bases are not the same, right? One's base 10, one's base E. So unlike B, where you had log base 10, and only one base E was the odd man out. I would convert all of those to base 10. Here you have your choice, because you just have to convert one of them. So when you have the choice, I would convert them to natural base. So let's convert log base 10 to the natural log. That's going to be the natural log of the argument over the natural log of the old base. What's the old base? 10. And then the other one looks good. Now in the denominator, natural log of 10 is just, in fact, a number. That's all it is. It's some number. So as I mentioned in class, just like x thirds can be written as 1/3 x, you can rewrite the first term as 1 over the natural log of 10 times the natural log of x squared minus 1. And then, of course, now it's minus the natural log of x minus 1. So now I have a number times the natural log minus the natural log. So now I'm ready to condense because my two logs that have variables are the same base. What's the first step in condensing if you have a number out front that's not a 1 or a negative 1? This second term has a negative 1 out front, so we're good on that. But this one has a 1 over the natural log of 10. So you got to bring that back up as an exponent. It's not going to be the prettiest exponent, but its mother still likes it. 1 over the natural log of 10. Minus the natural log of x minus 1. Now I'm finally ready to condense. I got a 1 natural log of blob minus 1 natural log of blob. So now when I condense, I pull 1 natural log out. Because I know I have a negative term, I know then I will have a denominator. The positive term's argument goes in the numerator, which is this whole fancy thing, x squared minus 1 to the 1 over the natural log of 10th power, all over x minus 1. And now you are done. That's it. Yeah. He would make a good NASCAR driver, would he? Out left, out left, out left. I guess we'll end on that note. All right, so tomorrow if you can come to class with the next section pre-downloaded and uploaded into Notability, we can hit the ground running, as they say. Have a great rest of the day. Enjoy your popcorn.